halves it. But what would happen if we did something like this to an exponent?
Let me leave off last time. We'll leave off. Guess last time we did IEEE stuff. It's the intuition from last time that float is basically equal to a it's like three things. It's like the sign bit and the exponent and the mantissa. And there was a small thing we did to each. The exponent gets subtracted by 127, and the mantissa, instead of being like one dot xxxxx whatever. Well, instead of being like x dot whatever, we like just hard code a 1 here, and then we do xxxxxx blah blah blah. So we looked at floats last time, and we'll see what happens this time.
Doubling an. So then you read what's written.
It's basically
representation, just scaled and shifted by some constants. So in some sense, the bit representation of a number is its own logarithm.
Yeah.
The intuition behind the second step is the following. Remind for this algorithm and for the rest of this video, it will be useful to think of the mantissa and the exponent as the binary numbers they are. If we are given two numbers, one being the mantissa and one being the exponent, 23 bits and 8 bits.
I feel like what he just said is important.
For this algorithm and for the rest of this video, it will be useful to think of the mantissa and the exponent as the binary numbers they are.
Oh yeah, just think of the mantissa and the exponent as the binary numbers they are, as opposed to, I guess there's like a few different ways that like the mantissa and the exponent, you know, for instance, you can think of it like this. So instead of kind of thinking of them in terms of raw numbers, you think of them in terms of like binary numbers. Yeah, I guess we'll see.
If we are given two numbers, one being the mantissa and one being the exponent, 23 bits and 8 bits respectively, we can get the bit representation with 2 to the 23 times e plus m if you...
No way, why is this quality? It's only 480p, what the heck? It's weird.
If you think about it. Because multiplying e by 2 to the 23 just shifts e by 23 digits. So that's how one could write the bits. But we get the actual number behind the bits with this formula. This should seem...
Yeah. We get the actual number.
Here to you. Here. behind the.
There's like two things.
So
this is one here. This is kind of like given the exponent and the mantissa. Given the exponent and the mantissa, you do this to basically get, this is like the float bit representation. So this is kind of like starting off the bit, and then you get the full float.
One could write the bits.
Just want to kind of write that. So it's just like 2 to the 20 times E plus M. This is just shifted over 23.
But we get the actual number behind the bits with this formula.
So this is, you like have the bits. Yeah. So this is basically you like chop off the 23 zeros and then you add this one back. And that's the actual number it represents. And then here, this is simple. You just subtract 127 and do times 2 to the thing. So I guess like E and M in both cases are the bits. And so they're kind of like the bits like by themselves, E and M. So if you want to get the bit representation of the float, you basically do 2 to the 23 plus M like this. And this like outputs a, what do you want to call it? Like a bits, I don't know, bits. It's like, it's outputs some B thing. B is in like B of 32. This is like a member of the 32. Like what kind of element do you get from this? The kind of element you get is a, maybe we should do it like this. You get a bit representation, which is in the family of like the 32 bits. It's a 32-bit thing. Versus if you do this thing, it's like 1 plus M over. You basically take M and you shift it down, and then you add 1 times 2 to the E, shift that down. And this gets you, this basically gets you like a natural number. Not a natural number. This gets you like a real number, I guess. So these are the kind of two fundamental like equations we got going on here. It's like 2 to the 23 times I guess the exponent is the exponent that gets shifted over and has these like zeros here, like implicitly. Mantissa is the longer thing. Yeah, just think of the exponent as like the short thing that's like to the left. It's like plus or minus the exponent and the mantissa. This is kind of a floating point number. Floating point number is kind of like a tuple. So yeah, if you want the bits. So this thing kind of starts with, like E and M and like outputs a bit. And then this equation here kind of like starts with the bits and outputs a real number. So just kind of getting the domain down, like this whole thing outputs a real number versus kind of like you just have E and M, and you take E times 2 to the 23rd, and then you add it to M. You know, that gets you basically 32-bit representation, 32-bit number kind of thing.
This should seem familiar to you. Here we have the exponent with 127 subtracted from it, and here we have the mantissa with the extra 1 in front. But now something completely different.
Just wanted to write out real quick, like kind of the, just one more small thing. You get kind of this like E, it's this kind of like small thing. It's this small E. And then you've got the mantissa, which is this like larger thing. Just think of it like that, like very small, medium, large.
No obvious reason at all. Let's take the logarithm of that expression. Since we're doing computer science here, we take the logarithm.
So this is like, yeah, so this is like starting with the bit representation. Yeah.
Base 2. We simplify as much as we can, take out the exponent, but then we get stuck. But not so the creators of Quake. Developer Gary Taroli knew a trick to get rid of the logarithm. You see, the trick is an approximation to log of 1 plus x. For small values of x, log of 1 plus x is approximately equal to x. If you think about it, this approximation is actually correct for x equals 0 and x equals 1. But we'll add an additional term, mu. This correction term can be chosen freely. Again, with mu equal to 0, this approximation is correct at 0 and 1. But it turns out that setting mu to this number gives the smallest error on average for numbers between 0 and 1. So going back to our formula, we apply our trick, as m divided by 2 to the 23 is indeed a value between 0 and 1.
It's like approximately this. All right, gotta go.